I'm looking across the Zoom rooms and I'm seeing so many different stream team volunteers at different stages of their stream team journey, from folks that were trained just last month to folks that were a part of our first crew. And I think we have every training cohort represented right now, which is absolutely amazing. And I just feel so appreciative to everyone for taking the time tonight to join us for a data exploration process. So as we're, getting logged into Zoom and having a chance to say hi to folks on the screen, want to set the stage a little bit for what we are up to this evening. So many of you, so again, with this diversity of engagement with the program, you all know that we like to start taking a look at the data after the first year, second year of monitoring. And so when you look at that wheel of engagement in the scientific process, some people think that data collection is the most fun. And some of us would argue looking at the values and discovering the story in your data might be the most fun. So it's really exciting to be here tonight to go through the starting steps of examining your data and seeing if we can identify some trends or explain why your creek is recording values the way it is. Before we hop into the presentation, I want to give a nod to some folks on the screen. So you'll see some familiar faces. We have Stephanie Letourneau and Phoebe Gallione, who you've seen a lot in workshops and trainings. We are also joined tonight by Alarm's founder, Professor Emerita at Dickinson College. We have Dr. Candy Wilderman on the phone with us. I love having the opportunity to learn from Professor Wilderman. So yeah, it's great to have Candy here. Also need to give a nod to the alarmies who are on here. We have Prerna, Michelle Hom, but have to give extra shout out to New Drong. New, can you give us a wave? I cannot describe how much time it has taken for us to get the data organized. And New spent a good portion of her winter break helping to get the first wave of data organized to a certain step. And then everyone on the alarm team has worked on the visualization process. And since then, New has started to write code in R to help make this process a little bit more streamlined for future stream team data interpretation events. So Phoebe will talk more about what the organization process looked like. But before we hopped into the presentation, wanted to make sure I gave some shout outs there. And I also have to give a shout out to everyone who is spending 5-6 hours a month doing stream monitoring, from calibrating those meters to washing your dishes and inputting your data into the Data Explorer. We are just so appreciative of your contribution to understanding the health of our streams in the Susquehanna watershed. And with that, let's go ahead and start moving into our workshop. So for most of you, you have had an opportunity to join an open call. We always like to get the chat box booming with some introductions. So we'd still like to do that. And we'd like to do our standard name, county, and the stream that you're monitoring. And why don't we add in how long you've been monitoring, either in months or in years. So let's get that prompt in the chat: name, county, site, and length spent monitoring. Okay, so here we are with our data exploration meeting. As always, we're so appreciative to our partners and collaborators. We can't do Susquehanna Stream Team without a family of partners, and we have folks listed here. Got to give a shout out to Master Watershed Steward coordinators on the horn, the River Keepers, and also have to get a nod to our funding, Chesapeake Monitoring Cooperative EPA, the Campbell Foundation, the Consortium for Scientific Assistance to Watersheds, which is Pennsylvania Department of Environmental Protection funding. So here's our agenda. We're going to be in our 2 hours together, if we're here for 2 hours. In the first hour, we're going to spend some time contextualizing the data exploration experience that we really see tonight as the first step in the process. starting to orient folks to the values and starting to understand what those mean. Stephanie will talk about people reporting out on their findings in June. And then the next step is starting to look at those site-to-site comparisons as well. So that'll be an opportunity down the path a little bit. So the first hour, we have a robust presentation, and then the second hour is open for Q&A after a short break. A general housekeeping, again, I'm seeing those introductions coming through. I love that. And especially while we're presenting, if you have connectivity issues and it's better to have your camera off, feel free to turn it off to increase connection. And if you can remain muted to reduce background noise and things like that. And please get those questions into the chat. There's definite spots in the presentation where it makes sense for us to pause and answer questions as we go. But like I said, the second hour of tonight's time together will be Q&A as well. So yeah, and with that, I'll hand it over to Stephanie.
Thank you, Julie. Yeah, so welcome everyone. We wanted to remind you of the program goals and what your protocol is aiming for. So, you've been collecting baseline water quality data. So we're trying to get a general understanding of the health of your streams. And you all have been using a standardized approach. That means anywhere from the upper to the lower Susquehanna, you've been following the same methods manual. All of the sites or all the counties that are in blue are the counties that have sites that have been monitored for a year or more. So those are the sites that we have organized data for and made packets. I have emailed out those packets with site summaries. They have graphs, and Phoebe's going to tell you more about that. And we will also share the link. But I do want to give a shout out to Lycoming and Clinton counties who had their first workshop in March a few weeks ago and is about to go through quality control. So definitely give them a warm welcome for being here. So this is the cycle monitoring. As a reminder, you might remember seeing it during your training. So we have gone through the study design, you've gone through training, we have gone through many quality control and data collections over the past year or more. And now we're at this part where we're doing data analysis, interpretation, and we're going to be diving into that with you, facilitating your own discoveries, and it'll help you with this next segment of data use and informing those local approaches to watershed health. So as a reminder, these are the parameters we've been monitoring. So water temperature, conductivity, pH, nitrate, nitrogen. You've been looking at the visual characteristics at your sites. What's your water look like? Are there any fish? And then in blue, I have here is water clarity and stage. Now, it's important to note that Columbia County actually started out with water clarity as it was part of their data goals. You'll probably remember that we are adding water clarity and stage for the entire monitoring manual. So it'll be part of the stream team process. And if you have been monitoring, we have an opt-in, opt-out approach for you. But this ties really well into this year 2 of adding additional parameters. So it says if the baseline data, need that further, if they say that there should be a further analysis. And I think that's important to look at now that we're adding water clarity and stage is, we've done data interpretation with Cumberland, and now we're revisiting, okay, what do we want to build out? And this is an overview of what Julie was describing for that data interpretation process that we're going to be doing. So about a week ago, I sent the data packets and we spent countless hours creating them. Right now, we're at our data exploration meeting. And then between now and June 8th, I know I've mentioned June 8th in emails, we're going to have data interpretation office hours. and also periods of times and resources for you to do self-discovery and look at your own data summaries and be able to find the stories yourselves and follow a guided prompts to figure out what's in the data. And we'll also have you create a slide with a summary of your findings. And we're going to give you a template with that. And you'll have the opportunity at this June 8th meeting to present then on your findings. So we're taking you through the entire process. We're building in a lot of time for you to be able to do that self-discovery and ask us questions. So without further ado, it's time for us to get started.
Yes, and one quick point that I want to follow up on that Stephanie said, a few of you have had initial data exploration meetings, the first group trained in York, as well as the Cumberland team last year. Folks that were a part of the Cumberland County meetings last year, you might see some similar content, but glad to see folks here to dive back into the process as a larger group. So thank you. And with that, now without further ado, Candy, please take it away.
Okay, so I'm going to be setting the stage for this interpretation in sort of a broad way. I want to get you guys thinking about what kinds of things might be impacting my stream, and therefore, and how might the data reflect the kinds of things that are impacting my stream. Next one. So what are the major factors that influence water quality in streams? And of course, there are many, but we can't cover them all. So I sort of picked out a few. The really important natural influencers are geology and climate. And the human influencers, some important ones are, of course, climate change, land use, which is manifested in terms of non-point source pollution, and point dischargers or point source pollution. Next. Okay, so let's start with some of the natural influencers first and see if you can see if this applies to some of your data. So let's do geology. Geology is extremely important in terms of determining the characteristics of your stream. Geology determines soil type and thickness. It determines slopes and landscape patterns. It is the primary determiner of ground to surface water ratios in streams. That is how much groundwater gets to the stream versus surface water. Drainage patterns are determined by geology. Some aspects of stream water chemistry can be explained just on the basis of geology. And geology basically determines the intrinsic suitability of the land or the limitations of the land for human use. Next. So here's a very generalized map of Pennsylvania geology, and the stars are the counties where Stream Team is currently monitoring. And this is looking at rock types. And you can see that it's very generalized, so that there's only a few major rock types. And there are the yellow, which is calcareous, which is the same thing as limestone. The sands and sandstones are sort of the brown, and the grays are the shales and the mudstones. And that covers most of Pennsylvania. In the southeastern portion of Pennsylvania, there's that green, and those are igneous and metamorphic rocks, and they shouldn't have too much of an impact right now on Stream Team's data, but in some cases they would be. Now, next, Pennsylvania is all geologic areas are divided into what we call physiographic provinces. And physiographic province, no, back up, please. Physiographic provinces are simply areas that have a common geologic history. And therefore that's manifested in a common topography, and they sort of look the same. So in Pennsylvania, we have the Allegheny Plateau. You can see that, if you could point to that. And that's in the western and the northern tier of Pennsylvania. That's consists of flat-lying sediments, and that's where our coal and oil and shale gas resources lie. Then in the center of the state, we have this thing called the Valley and Ridge. And the Valley and Ridge are these folded sediments where we have long ridges and wide valleys, ridge, valley, as we travel north or south through the Valley and Ridge. And most of us who are monitoring in the Valley and Ridge and Stream Team right now. It's part of the Susquehanna, almost completely in the Susquehanna watershed. And then finally in the southeast, we have the Piedmont, which is a more rolling topography, and that consists primarily of these, or a significant amount of these igneous and metamorphic rocks. Okay, next, please. So let's look at a couple of the rock types and delve a little bit deeper into them. So sandstone. Okay, sandstone is made up of coarse grains. It's mostly quartz, which is silicon dioxide. And silicon dioxide is very insoluble, meaning it doesn't dissolve well in water. So sandstone doesn't shed a lot of ions to contribute to conductivity. Okay, so it stays pretty much to itself, very resistant to erosion, mostly insoluble. And because it's resistant to erosion, it forms the ridges or the mountaintops. Things get eroded around it, but it stays. Next, here's some pictures of sandstone at the top of North Mountain in the Cumberland Valley. And you can see looking over the valley, the bottom slide shows looking at the view of the valley from the top. And so that mountain is made of that sandstone. Next. Okay, this is just showing an outcrop of the Tuscarora sandstone, which forms North Mountain or Blue Mountain. And there's a different kind of sandstone in York County, part of the northern Piedmont, which are red sandstones of a different age, and they're used very, very commonly for beautiful buildings down there. Next. Okay, so excuse me, typical sandstone streams, because they're on the mountains, they have thin soils, very steep slopes, high velocity and rocky substrate, a medium groundwater to stormwater ratio, very low conductivity because they don't shed ions, low pH, and they are often forested. So here's just some shots of typical sandstone streams. And so you can see that the geology is critically important in determining the characteristics of those streams. Next. Now we move to shale. Shale is a very fine-grained rock, very, very common in Pennsylvania. I guess its main characteristic is that it's rather impermeable to water. And of course, the shale gas plays in Pennsylvania are made of shale. Next. Okay, this shows the bedrock. In place of shale, it's very thin bedded, and it looks kind of like hardened mudstone. Next. Shale also is very fissile. It breaks up into pieces, and so it's easily eroded. And because it's easily eroded, it forms the valleys. So when we talk about these valleys and ridges, the sandstone is the ridges, and the shale is part of the valleys. Next. Okay, typical shale streams are in the valleys. They have low to medium gradients, low to medium velocities, muddy to rocky substrates, medium conductivity. They're very flashy because the surface, they tend to have a very low groundwater to surface water ratio. So the surface water comes straight off of shale and into the stream. So they're very responsive to rainfall events, up and down, up and down. And they're highly susceptible to runoff pollution. Next. Limestone. This is the last rock we're going to look at. Limestone is like the shales and the sandstones. It's usually formed in a marine environment, but it's formed through biological or chemical processes. It's primarily made up of the mineral calcium carbonate, and calcium carbonate, this is the key to limestone, is soluble in slightly acidic water, such as rainwater. Next. So this shows some bedrock outcrops of limestone, and you can see the solubility holes in them and the fissures that are widened due to the rainwater dissolving the limestone away. Next. So limestone is a great building block. We use it for barns and mills and college campuses. Dickinson's campus is entirely limestone, as some of you know, I'm sure. Next. They're militantly limestone, by the way. Okay, and Limestone is extremely interesting, and it forms very, very unique streams, as I'm sure most of you know. The main thing is because of the solubility in rainwater, whenever there are any cracks or fissures in limestone, they get eroded and they get enlarged. So when rainfall falls, it goes directly down through the ground into the groundwater. And then it moves through the groundwater and eventually emerges into the streams. And so limestone streams are fed primarily by groundwater. And remember, groundwater maintains fairly constant temperatures, fairly constant flow. And so the characteristics of limestone streams are entirely dependent on the geology. Next. Here's some pictures of typical limestone streams. They're in the valleys, they have thick soils, low gradient slopes, and a very high groundwater to surface water ratio, meaning the groundwater contributes more to the stream than the surface water does. And therefore, they tend to have a relatively constant temperature and a relatively constant flow. They're very high conductivity because this calcium carbonate that we talked about sheds ions into the stream. It dissolves, and the calcium and the carbonate ions contribute to the conductivity. They're used very, very commonly. Limestone areas are used very commonly for agriculture, and of course, more recently, they're being highly developed. Next. So this is kind of cool. This is data that was collected by the original Conneauguina Creek Watershed Association, or maybe not the original, but one early version of them, in 2001 to 2003. And these guys are your predecessors. They were a stream team of sort. And they collected temperature at a bunch of different sites in the Conneauguina Creek. The blue dots are the non-limestone sites, and the red dots are the limestone sites. And this is just temperature over a period of a couple of years. So if you'll, next, please. So this is the graph showing the blue sites and the seasonal variations in the temperature. Next. This is the graph showing the red sites, and the red are the limestone sites. And you can see that the temperatures of limestone in the limestone creeks have lower highs and higher lows. In other words, they're dampened and they're more constant. So next slide, please. So that kind of temperature regime and flow regime, also the flows are fairly stable as well, lead to a whole unique flora and fauna in limestone streams. The flora are very often plants that love calcium or calcium loving because there's so much calcium in there. The bugs are sow bugs and scuds or crustaceans, they're dominated by that rather than most streams are dominated by insect larvae. And that also has to do with temperature fluctuations. And then finally, of course, limestone streams support cold water fisheries like trout because they don't get too warm in the summertime. They don't get too cold in the wintertime. So it's a great environment for fish that are sensitive in particular to warm water. Okay, next. Okay, so I'm going to show you some data that Stream Team folks have collected that reflect, that I believe can be explained on the basis of the geology of the area, to just show you that it in fact is a factor. But before I can do this, I have to real quickly introduce box and whisker plots. I don't know, how many of you, hold your hand up if you know box and whisker plots? Okay, I can only see a few of you, but okay. All right, well, I'm gonna do it, I just bear with me, I'm going to do it very quickly, and I hope it'll work. Okay, a box and whisker plot is a plot that shows all of the data in one figure. It's like a cartoon, one figure. Okay, so this is perhaps it's the data that you've collected on conductivity over a year. So there's 12 different points, and you want to see it all in one graph. Okay, the maximum value is the whisker, the top whisker, as you can see here. And the minimum value is the bottom whisker of all the data you collected, okay? And the median value is your central value, and that's the X here, and that's in the middle. Now, the box is the tricky part. The box is one of the interesting parts. Within that box, there is 50% of your data, okay? So that box is designed so it holds 50% of your data. So if that box is really tall, that means that your data varies over a very wide range. So it's quite variable. If that box is very short, that means your data is not variable. It's very constant. It hardly varies at all. So if you look at, and it's already been pointed out, thank you, Phoebe. If you look at the blue one here, you can see that it's got a lot more variability than the stream that's represented in orange, whose data is represented in orange, where there's hardly any variability at all. In addition, you can see that the stream whose data is represented in orange has higher conductivity overall than the stream that's represented in blue. I mean, even the maximum blue is even lower than the minimum orange. So very different streams, correct? Both in terms of variability and also in terms of the actual values, the median values, the maximum and the minimum. Okay, so let's go to the next and we'll use these. All right, this is data that was collected by Stream Team on the Conneaut Creek. And it really, I think, shows beautifully the role of geology. Each box and whisker is a different site collected on the creek. The limestone streams are on the left-hand upper side, and look at those box and whiskers. Okay, they're very high up, high conductivity, and they're very low variability, right? They're short, as opposed to the main stems sites, which are there. Those are lower in terms of conductivity, and there's much more variability. So that shows exactly the impact of limestone. What we're seeing here is limestone, constant, very high conductivity because it's soluble, but also relatively constant because it's groundwater. Mixed geology is not as high in conductivity and it's all over the place. It's variable, okay? And the only site in the Conneaut that came close to being at the same level that the limestone streams were was a highly urbanized stream. And we'll talk about that in a moment when we talk about land use. Okay, next slide. Water temperature, same thing. Is it geology? Well, look at the limestone versus the mixed geology sites in the Conneaut. There's less variability, no question about it, in the limestone. Now, the only true pristine limestone site was that orange one. The other two sites are actually being impacted a little bit by certain kinds of land use. And so that's one reason they might have more variability. But it definitely shows the same kind of pattern, less variability in temperature. You can certainly attribute that to limestone. Okay, so you have a reason that your data looks the way it looks, which is what we're trying to find. Okay, next. All right, how about climate? Climate is very complex, and it determines the complex flow of streams that we have, which is a function of precipitation, evaporation, groundwater recharge and runoff. Climate determines the rate of weathering processes, the formation of soil. Climate determines the temperature of streams, and climate determines the ecological composition of streams and watersheds. Sorry about that. Next, please. Next, yeah. Okay, so let's go and let's switch into human influencers. And of course, there's climate change. And we won't get into this much, but leave it be that climate change can threaten aquatic ecosystems in extremely serious ways, increasing stream temperature, altering stream flow due to drought or increased storms, and also worsening other stressors. Increased storm runoff, including nutrients, pollution, and sediment. And so it can really turn ecosystem health on its upside down. Developing a database on stream temperatures and flows is critical to understanding climate change. And we sometimes volunteers say, why am I collecting stream temperature? I mean, it's just showing up and down like air temperature. Actually, that's a really critical piece of information that you guys are collecting, because in the next couple of decades, that's the kind of information we're going to rely on to understand what's going on in terms of climate change in streams. And adding flow, or at least a surrogate for flow to our measurements, is also going to help us in terms of understanding the nature and the magnitude of the climate crisis. Next. Land use. Okay, this is a big one. Land use impacts streams. What's happening primarily in most places, including Pennsylvania, is the conversion of land from forested to developed or agricultural land. Now, what does this do? This decreases land permeability, which changes groundwater to surface water ratios. So it affects flooding, it affects drought, frequency and magnitude. Land use disrupts the drainage patterns of streams. It alters stream ecology due to the removal of forested riparian zones. It alters stream chemistry due to the runoff of pollutants. And it increases stream temperature due to the urban heat island effect and the removal of shade trees. So land use conversion has a major impact on streams. And I maintain you're going to be able to see this in your data as you look at land use and the relationship of land use to your data. Next. Generally speaking, the four chemical kind of parameters that we're doing, temperature, nitrogen, nitrate, conductivity, and pH, are affected by both agriculture and urbanization. Agriculture has a severe impact on nitrogen nitrate as they put fertilizers and conductivity with liming and other chemicals that are put on the fields. But urban and suburban also have a moderate impact in terms of nitrogen nitrate and moderate to severe in terms of conductivity. Temperature, urban and suburban, has a severe impact because of the paving and the heat that comes off of pavements. Both of them have only a slight impact on pH. The real severe impact on pH are acid mine drainage and acid deposition. Okay, next. Okay, push again. Okay, so in our area, and I suspect in your areas as well, the land conversion is going from rural and there's a lot of trucking activity in our area, and there's an awful lot of land that's being consumed by warehouses and trucking activity. It's quite phenomenal. Next slide. Okay, these are 3 photographs. The first one's from 1937, and you can see that road going through there. That's Route 11, and you see the Cana de Gwinnett. There's a little meander of the Cana de Gwinnett there. Okay, and you see the farmland everywhere. 1971, you've already got the Turnpike and the Route 81 put in there, and you're beginning to get some development in what we call the Middlesex area with some trucking activity. 2018, look at the extent of those warehouses and the trucking activity. And basically, it's just consumed all of the farmland. And this is just east of Carlisle. Next slide, please. Because we ran out of farmland east of Carlisle, the trucking industry has moved west of Carlisle, and look at the amount of land, and there's even construction shown here that's going on today in the western part of Carlisle. So that's a major conversion. Next. The other conversion, hit it again, please, is going into housing developments. Next. Next, please. Okay, and now again, you've got the same set of aerial photographs, 1937. Note the red star, because the red star gives you a point of reference. That's the Cana de Gwinnett that's meandering through that beautiful farmland in 1937. Look at the extent of the development along the West Shore that happened in 1971. And finally, in 2018, you're really hard pressed to find a farm. So that kind of land conversion is going to impact your stream water chemistry. And that's why one of the things in your data packet is showing the different land uses in the watershed upstream from your site. And it's very, very important to look at that. Next. Okay, so let's look at 3, these are non-carbonate sites. So there's no limestone involved here. In the counties that you guys, this is recent data that's in your packages. So Lackawanna, Leggett's Creek, look at the land use there. That pie diagram shows 28% developed, 18% ag, and about a little more than half natural area. All that developed, that's a lot of developed for a watershed. And look at the conductivities. The median is 492, the maximum 992. These are microsiemens per centimeter. That's a really high conductivity. Okay, now we go to similar geology watershed in Luzerne, Abrahams Creek. And notice how the land use is different than the Leggett's Creek. It's only 5% developed. The agriculture is 39%, and natural area is about the same. And look at the drop in conductivity with that drop in developed land. Okay, with a median of 164. And then finally, we go to Kitchen Creek. I don't know where these places are. I wish I did, in Luzerne County. And Kitchen Creek is almost 100% natural. It's 99% natural. And look at the conductivity readings we have there, 34.5. So we're really looking, since we're holding geology relatively constant, we're really looking in your data at the impact or the difference, the impact that land use has. So you should be able to see this. Next. I'm going to go to the next one. Okay. Now let's compare. What we did here is we compared multiple sites within a watershed in regard to the impact of land use. So we have, this is in Cumberland County, we have the Conneauga pie diagram, and we have the Yellow Breeches pie diagram. Okay, and we looked at all the sites and we looked at the average land use in the watershed. And you can see that the Yellow Breeches has quite a bit more natural land than the Conneauga. Conneauga has a lot of developed, a lot of agriculture. Yellow Breeches, a moderate amount of developed, a moderate amount of agriculture, and a lot of natural land. And if you look at the diagrams on conductivity and nitrate, if you could, the Conneauga are blue and the Yellow Breeches are orange. And if you remember how to look at these box and whiskers, you can see the Conneauga conductivity is higher significantly than the Yellow Breeches conductivity, and the nitrates are higher than the Yellow Breeches. And I suspect, since the geology is fairly similar in terms of the ions that are available to make conductivity, that at least a good portion of this is due to land use, differences in land use. Next, please. Okay, and then finally, the other impact on water chemistry or water quality are point dischargers. And point dischargers, I think Julie's going to talk about it a little later. They're actual discharges that come out of a pipe from industries or municipal wastewater treatment plants. They have to have a permit. They have to be permitted under the Clean Water Act. And the permit sets limits on the amount of pollutants that they're allowed to put into the creek, and also the flow that they're allowed to put in. The discharge, what they actually discharge, is monitored by the company itself and submitted to DEP. The permits can be accessed by the public, and now they can be accessed online. You used to have to go down to the DEP office and make an appointment and have them Xerox all these permits. Now you can actually access them online, and it's wonderful. We can show you how to do it. And point discharges, of course, may impact water chemistry. Next. For example, this is the Yellow Breeches. The red dots are the three major point dischargers in the Yellow Breeches watershed. They're all wastewater treatment plants. A major discharge is defined as more than 1 million gallons per day. So these are those three. Next. This is what a permit looks like. A lot of numbers, but it's really fairly simple. It tells you how much they're allowed to emit using different kinds of units, how much they have to monitor, and so on and so forth. The red is the nutrients that are coming out of this is the South Middleton Township Municipal Authority. And next slide. And you can actually plot how much is going into the Yellow Breeches based on the permits. And as you can see here, the Yellow Breeches, as we said, has 3, if you want to point those out. And the Conneauga actually has 7 major wastewater treatment plants. And those bars there are the amount of nutrients that are going in from those facilities. And so you can see the Conneauga has quite a bit more load than the Yellow Breeches. And this is something that also may be contributing to the fact, not only land use, but also point dischargers, to the fact that conductivity and nitrates are higher in the Conneauga than they are in the Yellow Breeches, probably both. To really analyze a point discharge, you have to evaluate, to look at its impact, you have to evaluate both upstream and downstream from the point discharger to make sure that it's the point discharger that's having the impact and not just generalized land use. Okay, so those are some ideas of things you can think about when you're thinking about why your data look the way your data look. Okay, next. Okay, so there's no question our data have a story to tell. The question is, can you read it? Can you figure out what it is? And understanding the local natural influencers as well as local human influencers is the first step and the key to explaining any patterns that we see in our data. Okay, next. I think it's Julie's turn.
Awesome. Oh man, Candy, thank you so much for walking us through the water quality influencers. I always glean something new as you're going through that. And I added some chat conversation in there. We have a few folks on today's calls whose sites were called out. So check the chat. And we also add some bonus points to the fact that folks were able to identify the Gladfelter paper plant in one of your pictures. So so thank you so much, Candy, for setting the stage for us. The other thing I wanted to point out before we get into water quality standards, Candy did mention the role of point dischargers in influencing our results. That is one set of maps we did not get to before the packets went out, but is on the queue to come out before the next data meeting. We made all new maps for the data packets. So that was a big task to do that, but those will be coming. All right, so let's start getting into the water quality standards. And as you all are listening, if you have questions and you're starting to pull up your data packets, be sure to write them down or go ahead and put them into the chat, and we'll get to those in a little bit. So as we talk about water quality standards, it really starts with the Clean Water Act. The Clean Water Act was passed in 1972. So actually this October will mark 50 years since the passage of the Clean Water Act, and there's going to be a series of celebration, as well as the EPA is going to be doing a lot of informational webinars starting this summer that talks about how far we've come with clean water, as well as how far we still need to go. So as we learn about those, we'll go ahead and share. So as a broad sweeping goal of the Clean Water Act, it is to restore and maintain the chemical, physical, and biological integrity of our nation's waters. And you'll note that right there, those buckets, chemical, physical, biological, are the same buckets in which you monitor, or for those of you who have yet to do your macroinvertebrate training, will be monitoring. So as a part of your monthly monitoring process, we have a combination of chemical and physical indicators. So we have a lot of goals associated with the Clean Water Act. Like I said, first and foremost is to restore and maintain the integrity of the waters. And that's really contingent upon this classification that is given to water bodies and water body segments that highlight what is the optimal use of this water body based in large part on those geological characteristics, as well as a few others as well, biological as well. The other goals associated with the Clean Water Act really is to focus on minimizing degradation. So as new development is coming in, as those warehouses came into the greater Carlisle area, one of the things that was a touch point as those were coming in was the fact that we have an exceptional value, exceptional value stream of the Letort. And that was going to be producing a lot of stormwater runoff that would be coming into the Letort in certain parts of that. And so as those developments were going in, measures needed to be taken to help prevent the degradation of the Letort at those sites. So one of the ways that the Clean Water Act gets translated into Pennsylvania language, so Clean Water Act being a federal act, in Pennsylvania, we have Title 25 that looks at the water quality, as well as Chapter 93 that sets those standards. And so I pulled this quote from Chapter 93, and again, the goal being to protect existing in-stream water uses and the level of water quality necessary to protect the existing existing uses shall be maintained and protected. So as you look at the Pennsylvania Code, you can check that out. Now, there's always this interplay between the federal requirements as well as what the states do. And so there's a couple of things for y'all to know. Every 2 years, it's on an even year basis. The state has to do a water quality inventory. This is the integrated report that Pennsylvania Department of Environmental Protection puts together, and it highlights two different things. One is looking at that water quality inventory. What is the status of our streams? That's 305B. And then we're looking at the list of impaired waters. What water segments or water bodies are not meeting their intended use? So those come out in one report, and I'll drop the links to the latest reports when I'm done. The other things that the states need to do is they need to, track their permitted discharge, keep permits, summaries of those discharge monitoring reports that Candy talked about. Again, that's public information, right to know. You can look at the discharge monitoring reports. Sometimes it requires going to a regional office to look at them directly if they're not already listed on a website. That is, again, a list that the state maintains. And then the other thing that happens at the state is they review those water quality standards that are listed in Chapter 93, which we'll get to in a little bit, every 3 years. So for those of you who have been engaged in Susquehanna efforts over the years, you know that there's been indicators that have been suggested to be put on. And that was an effort of the Lower Susquehanna Riverkeeper looking at our smallmouth bass. So every 3 years, we're looking at those water quality standards and identifying, what needs to get judged up and changed or elevated there. And again, they have to make the integrated report that covers those 305B and 303D elements publicly accessible. And again, I'll drop those links when I'm done chatting. So those are some of the requirements. And again, looking at that interplay between the federal rules and how that gets implemented at the state level. So one of my favorite books or resources in the alarm office is our copy of Chapter 93. It's also available online. Again, we can drop these links later. And this is where you get to see what the water quality criteria are, looking at use and looking also at the water quality standards that have to be maintained with these different uses. So let's talk about how we find those types of things. So I know these maps look really dated. I just want to say this is not an alarm map. This is coming from the state, but the state is broken up into these different regions. And so when you're looking at Chapter 93, and thank you, Phoebe, and you're trying to find what the different designated uses are of your stream, you want to first find your region. You're going to find, and think about it as like a reverse, or think about it as a watershed or address. So here we are at Dickinson College. We drain into Letort Spring Run, which flows into the Connequent, then the Susquehanna, and then the Bay. So what we would do when we look at trying to find the designated use, we would start with the Susquehanna, then we would go to the Connequent, and then we would find the tributary of the Letort Spring Run and then find its designated use. So let's look at a couple of examples. So the first one we've got, I knew Tina and Jeff, you were going to be joining today. So I pulled your site as an example. So Tina and Jeff are part of the York Stream team. And again, if we were to do a reverse watershed address, they actually have two sites, Doe Creek, which drains into the Bermudian Creek. They also have a site on the Bermudian Creek, and the Bermudian Creek drains into the Conewago Creek and then into the Susquehanna. And so you can see when you look at Chapter 93, Tina and Jeff, that your state standards are in your watershed are warm water fishery. And you also have a migratory fish designation as well. Let's look at another example here in Cumberland. So one of the two large watersheds is the Yellow Breeches. We have close to 10 sites, I believe, that is on the main stem of the Yellow Breeches, as well as several tributaries draining into it. And we have these, I guess we have 10 sites total. But anyway, it's a half on the main stem, half as tributaries. And you'll see you have a wide range of designated uses. So the most restricted standards are associated with exceptional value, and that's only for cold water streams. And then you have high quality cold water fisheries and cold water fisheries. And then we also, and for everyone to know, we have warm water fisheries and high quality warm water fisheries. But you'll see that the Yellow Breeches watershed has a great cross section of designated uses. So once you know what your designated uses are, you got those numbers, you got those codes. So what are the values associated with that? Now, not all stream team parameters that we monitor on a monthly basis has a state standard. So again, this is being pulled from the Pennsylvania Code Chapter 93, which Phoebe dropped the link to. At the very bottom of the screen, you can see the standard for pH. And pH is a nice range actually for all designated uses. So it doesn't fluctuate as much, but as we'll see on the next slide, I think it's the next slide, we do get to see some differences with some of the criteria as it relates to temperature. So again, for water quality criteria, pH, we have that state standard 6 to 9. Feel really good about a lot of our sites and stream teaming with that. And then with temperature, and this is one of the reasons why we have you all measure in degrees Celsius, having those Celsius standards here. You'll see that difference. And, reflecting back on what Candy was talking about, limestone streams and their very narrow box and whisker graph and range. And you can really see that in relationship to the warm water fishery. So typically streams that have that WWF, not World Wrestling Federation, it's not that WWF, it's a warm water fishery. You'll notice that we have that nice wide range, which shows that fluctuation of values as it relates to the seasons. And you do see a lot of limestone streams being a part of that cold water fisheries as a result of those limited temperature range and all the reasons that Candy highlighted as to why those streams maintain that nice constant temperature. So we do not have a state standard for nitrate, nitrogen. And actually, I don't think there's a state standard for water quality criteria for any of the nitrogen values. So we don't have a state standard. We do know that the background levels of nitrate nitrogen are 1 part per million. You'll notice some of you have very flat bar graphs that we were thinking about after we sent them. We're like, maybe we should use a different graph so that you knew that you didn't have 0 values of nitrate. It was just you all had 0 as your value. So some of your nitrate graphs looked as though you haven't been monitoring, but we know you have been and just got values less than 1. So that's reflective of background levels. One thing we like to use as kind of like a threshold is knowing that the drinking water standard for nitrate is 10 parts per million. And we start to raise an eyebrow alarm personally. I, Julie Vastine, start to raise an eyebrow when I see values above 5 and 7. So whatever you want to take that as a read on that, there you go. But there isn't a state standard for in-stream criteria. And with conductivity, also there isn't a standard, and that is in part related to the fact that geology and the play of the calcium carbonate constantly dissolving, we do have elevated conductivities. But one thing that we do know is in the state, freshwater streams tend to range 0 to 1500. We were just talking to a group up in Erie, Pennsylvania, and one of their sites has got industrial discharge, and they have values of conductivity close to 5,000, not an AMD stream. But yeah, so for folks that do have AMD up in the middle Susquehanna and with industrial discharges, you'll notice that elevated conductivity, and that's outside of that range you would expect for freshwater systems. So as we move forward from looking at those water quality criteria, there's a couple of things and resources that you can check out. And again, these are things that we can look at. I'll drop the links so you can explore this on your own. So you can find this map that's connected to the integrated report. There's a couple of different layers. The next slide shows a layer of the different impaired streams. It doesn't look like super exciting. This isn't Yellow Breaches. Some of your larger watersheds, actually, watersheds throughout have some impairment. And that was one of the criteria we wanted to pull out in your data packets. So you'll notice with your site profiles, as Phoebe will walk us through, we have that percentage of land use, we have that percentage of geology, starting with those key influencers of water quality. We also have your designated use, and then you can look at the different state standards associated with those designated use. And then if your site was in a stream segment that was not meeting its designated use, it meant that it did not meet one of those 55 plus criteria of the state standards, it then tips over into being considered impaired. And then we listed why it was impaired. So we do have a number of sites, for example, that are impaired from bacteria, impaired recreational, and different things. So we included that as a part of your site packets. So you know that is a part of your site's profile. So that is, we could spend hours talking about water quality policy and looking at how this informs our interpretation today, but being able to get a sense of the policy, getting a sense of the lay of the land. We don't have state standards for all of our parameters, but we're still able to dig in and find a story of some interesting elements, especially as we bring in the geology and land use, as Candy discussed. And with that, I'm going to hand it over to Phoebe to talk about the data to information process.
Thank you, Julie. So we've talked about the influencers to your stream. We've had a chance to look at some of the policy, but now let's look at your sites themselves and a primer to them. So the data organization process took months and months, but the entire process can probably be summarized in these 4 steps here, and we'll go into them in just a moment. You can go next. Awesome. So the first step was raw data. So we downloaded your data from the Data Explorer. And the first thing that we did, we isolated the parameters that you were looking at, which you can see here: conductivity, nitrate, nitrogen, pH, water temperature, and for some of you, water clarity. And the first thing we did was look for errors. So there are different kinds of errors that we looked for. One thing being precision errors. So precision errors come in when a value is recorded that is more precise than the equipment can read. There are 2 examples here that I put in manually, so this was not, I fixed the data here a little bit. So you can see 2 examples here under conductivity and nitrate nitrogen in yellow. For conductivity, we know that the pocket testers don't read decimals above a certain value, so you wouldn't be able to get that one there. And then for nitrate nitrogen, this could be a rounding error, but when you round, it also still needs to read a value that the equipment can read, so that would also be considered an error. Another error you can see are data entry errors. I don't have an example here, but one example could be if you consistently usually get conductivity values in the 400s, and suddenly there was a value of 4. We might be able to guess that, oh, perhaps the rest of that wasn't typed in correctly, and we'll be able to go back into the data sheets that you upload and check to see if that's true, or I'm sure a lot of you have gotten emails in the past couple of months, and we'd be able to verify with you as well. The last type of error that we looked at were unit errors, which you can see all the way to the right here with water temperature, which is recorded definitely in Fahrenheit than Celsius. So we were able to look at all these errors, highlight them, and we were even able to fix them in the Data Explorer themselves. So if you were ever to go back and re-download the data, those errors would no longer be there. So we can go to the next step. So once all the errors are out of there, we can then summarize the data. So we took all of your data and we pulled out a couple of the statistics that we thought would be interesting. So we looked at the maximum, which is the largest value you'd see in any category. We looked at the minimum, which is the smallest we see in any category. And then we looked at the median. So for anyone unfamiliar who just needs a refresher, the median essentially finds that central value without the skew of rare outliers. So you would line up the values in order, cross them out from most to least, and you get this middle value, and that's what our median is. So we pulled those out for you as well. And then we made graphs. So raw data is wonderful. It's great to see actual values, but it is so much easier sometimes to see the variations and trends in the data when you're able to see it visually. So we made graphs for all the parameters. And the graphs are all laid out the same way, with the parameter on the y-axis or the vertical axis, and the months monitored on the horizontal axis there. And as you can see, this is an example that I pulled out specifically because of the trends that you're able to find. This one's a beautiful water temperature bar chart and shows the warm temperatures in the summer months and the cold temperatures in the winter months. So that is something to look out for in your graphs. And now there's one more step in this process, which lends itself to what we're doing now, and that is the interpretation step. So in order to make this interpretation easier, we also pulled together considerations and site information, that a lot of which is in the form of a map, and could cover land cover, geology, designated use, or stream impairments. So that's a process that we took to get to this point. And now we pulled it all together and put it into lovely data packets, which you should have received last week. So for those who might not have had a chance to look at it, or those who just want to walk through it together, let's look at what's in those packets. So each site has a unique set of 3 slides for themselves. And so we'll walk through these 3 slides quickly. The first slide is going to be the site profile slide, which you can see here. It'll have a map with your site specifically circled in red so you can find it. There'll be a list of site information we can see here on the left. For example, the first one is drains, which says how much of that watershed falls into that specific point. And then it has a lot of the other points that Candy had introduced and Julie had introduced us to previously. And then we also have a land use pie chart, which we put in here because sometimes it's just easier to look at a pie chart than it is to look at percentages and be able to visualize it. So we stuck that in there as well. And then the next part of your profile will be the bar graphs themselves. So for some cases in Columbia specifically, we have some sites that'll have 5 bar graphs. So there's a chance you'll have an extra slide so you can see it easier. But in general, you'll have a slide that has the parameters that you were looking at from the point that you started monitoring and the point that you stopped monitoring, or at the end of 2021. And because Julie mentioned before that there are times where on the bar charts, the 0, you don't know if it's a 0 value or if it's a time that you didn't monitor. We also included on the 3rd slide, which you can move to, the raw data. So if you're interested in looking at the specific numbers, or you do want to see whether that's a 0 or a time that wasn't monitored, you'll be able to check that out here. And on this 3rd slide will also be the summary statistics that I just walked us through. So those are the slides that will be unique to your site specifically, and you're welcome to look at the other ones, but those are yours. And then we also have one more part of these packets, which are these supplemental maps, which were a huge part of it. And as we're seeing, there's a lot that goes into interpretation, and having context is a big part of it. So at the back of your packets, you'll have maps for geology, land cover, stream impairment, designation, and you'll also have a map with subwatersheds to give even more context to the your sites and the information. So that's what you'll find in your packets themselves. However, I don't want to just give that to you and run with it. So let's go through a couple examples and a couple things that you can look for when interpreting your data. Of course, there are so many things you can look at, so we're only going to isolate a few. You'll have to figure some out yourself. So this site is Kings Gap Run, and this data for the 2 examples that we're looking at is data from last year's data interpretation meeting, so the data is not quite as current. But this is Kings Gap Run in Cumberland County, and I want to draw your attention at this site specifically to geology and land use. So this is one of the few sites that has that igneous and metamorphic geology. And also for land use, as we can see, it is almost completely natural, which does make sense. It has a very small watershed in the middle of the woods. So you do have a lot of that natural area that's very small developed. So let's look at the data that came from that and see what stories we can find. All right, so first, if you had a chance to look at your own data, this might not be what your graphs look like, especially with nitrate here in the bottom corner. As you can see, there are no bar graphs that you can see, and I promise you that's not because of lack of monitoring, but because the values are in fact 0. And one thing, if I was going to look at that, a story that I could say is, we noticed that the land use was primarily natural. There really wasn't any agriculture. And as we walked through before, agriculture and urban environments are a lot of the reasons that we have nutrients in the water. So the fact that it's almost all natural can be one reason why we're seeing essentially background levels of nitrate, nitrogen in the water. So that could be one story we pull out of this data. If we were going to think about geology, we can turn to pH. So this site, if we remember a moment ago, is igneous and metamorphic. Candy talked earlier about how limestone streams are the ones that have this wonderful buffering capability, where the limestone will dissolve and buffer some of this pH and make the water more basic. But we're seeing that this site is quite acidic. It has a pH of 6, which is still within that regular range that we had talked about, but it is still quite low. And because it is natural and because we don't have that limestone, maybe we can say that this is due to Pennsylvania's history of acid rain. So there are multiple stories you could pull out of pH. And then if we're going to go to conductivity, this also is going to be something that a lot of you probably won't see at your site. Last year, this was in fact our lowest conductivity site, which is quite interesting. And it could also be pulled, you can also pull geology into this in the sense that limestone dissolves and puts ions into the water, whereas your igneous and metamorphic rocks really aren't going to dissolve and put those ions in the water the same way. Additionally, we can look at land use again and note that the natural environment probably won't show as many sudden spikes of conductivity as you would in an urban environment, say in the winter where you might get road salts or other influences like that. So even just looking at land use and geology, we were able to pull out so many different stories at this one site. And I'm sure there are more if you took the time to do so, but I'm going to show you one more example. Oh, sorry, and this is the raw data because I did want to prove the fact that those were in fact zeros if anyone couldn't believe that that site didn't have nitrogen values there. So we'll go to our last example here. And this is Yellow Breaches at Lower Allen Community Park. And you can see the site circled as well. So this time I want to look at the stream designation, which we just talked about in our policy section. So this site itself is designated as a cold water fishes stream, which means that if you recall, this stream should not exceed or go outside of a 3 to 18 degrees Celsius barrier. And spoiler alert, if we go to the graphs on the next slide, we'll see that that's not quite the case. You might recognize this graph from a few slides ago, but you can see that as you hit the summer months, the values are going upwards of 22 degrees Celsius, which is, and it's consistently doing so. This isn't something that only happened once, which means that we might have to call into question whether the stream designation could really be upheld. And you can contribute multiple things to why this is happening. It could be climate, it could be because of maybe a dam being put up by the site holding up water. There could be many reasons and stories, and you'll know the context to your stream better than we will. So we'll be interested in seeing these stories that you can pull up based on what the context to your sites themselves. So, and then we'll look at the raw data here. And I just went ahead and highlighted the times of the year where the sites did exceed that temperature range. So we only went through a couple of the potential things you can look at, and excited to see what y'all pull out of your data. I think now you're going to...
So thank you, Phoebe, for walking through that. That was fantastic. We try to do a diversity of site profiles throughout the presentation, covering the whole watershed. If you'd like to see what you would like to explore with your data, this is really an open space to either ask questions about the content that you just heard to dive in a little bit deeper, or taking a look at your sites and see what questions you had coming into tonight's meeting. So feel free to unmute yourself or use the raise hand function using the reactions, or type the question in the chat. But we're a small enough group that we can, put out your questions as you have them. Yeah, Greg John. Yeah, and you're muted, sorry.
No, I'm not. Looking at the maps, and I think this is probably the first monitoring meeting we've had since we stood up the site at the Oars Bridge Spring. Yeah, I see Stephanie shaking her head, so we're good.
Oh,
Okay.
yes. Yeah.
Where, maybe you said this already and I just missed it, or I was looking at something else. Where does the site information actually emanate from?
Oh, that's a really great question. So one of the things we
And
can
I'll
do.
follow up with another question on that too, so go ahead.
Oh, okay. Let me take a quick moment to pull something up on my screen so I can share it. So hopefully you all are seeing an example. This is Jeff and Tina. Your site happened to be up on my computer. So when we're to receive the information about things like your stream designated use, as well as the land use information, and also looking at the impaired status. The way we did that is we used the information or the metadata associated with some geographic information systems, which enables us to map this out. So one of the things that you'll notice on the maps is that there are data sources at the very bottom. So this map here that's showing site locations is actually pulling data from diverse points. We have road information, we have waterway information, and then a couple other elements as well. And so when we put your site into the map, we can look at the data of that site based on those layers behind it. So there's an Excel file that we can look at to help get really quick answers of, what is your designated use at your site, as well as, information about whether it's impaired, and things like that. Now, the tricky part, and took some very sophisticated mapping elements, was actually coming up with your drainage area and developing what is called, or just establishing your watershed. And that then got applied to geology layers and things like that. And I wonder, Candy or Phoebe, or Stephanie, if one of you want to talk a little bit about the watershed delineation process, and then how we took that information and put it on top of the GIS or the geology and land use layers. Or do you want me to keep doing that?
Yeah, I mean, a lot, it's done through GIS. And there are models that have been created that that delineate watersheds based on topography. And it looks at, to try to see the line where all the water on one side of the line goes in one way and on the other side of the line goes the other way. I mean, basically, and it's a GIS model that I think Stroud Water Research has a similar model. I think, Dickinson has a model that we've been using. And it's just a reiterative process, basically, that defines the watershed. It's pretty complicated. I mean, to actually create that model is really complicated. Once it's created, you can push the right buttons and use it. But, and the nice thing about that then is that then once you get your area delineated on GIS, then you can put that on, as it were, on top of a land use map, and clip your watershed and determine then what percentage goes to what land use. And these land uses have been lumped. There's actually many, many more land uses, but we lump them into, 3 easy uses, just because it's much more tractable that way. But anyway, I mean, that's the best I can do. Maybe somebody else.
Yeah. Thank you, Candy. And so it's really fun when you take a look at all the different sites, and we have really great watershed representation or sub-watershed representation throughout the watershed, throughout the Susquehanna watershed. And so it's fun. You see examples like Linda Hartzell, who's on, where her site is on Deer Creek, that is draining 5 square miles. And so as Candy was saying, at the bottom of your packets, you can look at the land use and things like that. So then that small watershed layer gets applied to that. And then we extrapolated the percentages of land use and geology from there. So it was a combination of looking at the maps from from what you get here with these visuals, but a lot of the information that we pulled was actually the data behind the map that we brought into your site profile. Great question, Greg.
Well, and the reason I asked that is, and I can see where we're sampling, if you will, midstream in the middle of some creek or whatever, some body of water. That all makes sense. In this case, that spring is coming right out of the hillside. It's surrounded by virtually 100% developed area, and it's interesting just to look at. I mean, I recognize how with you got that metadata all together. It just didn't seem to apply to me in this particular situation because the site is so specific. I'm monitoring about 20, probably 15, 20 yards downstream where it pours out of the hillside.
Yeah, you definitely have the smallest watershed delineation of all. We'd have to look and see who has the largest watershed, but or drainage area. But that'll be a fun fact that we could bring into the Susquehanna Stream Team Facebook group. Great question. So I want to turn our attention to the chat. Mark Lentz asked the question: can a stream have 2 designations? Or can a designation change from the headwaters to the mouth? So at your site, yes. So let's start with the second part of your question. As your stream is going from your headwaters to the mouth, and especially for our larger watersheds, and that was the example I was trying to highlight with the yellow breaches, is the entire watershed itself actually had 4 different designated uses within it. So it can change. And the yellow breaches is really interesting, as Candy pointed out, like you have half of the watershed in limestone, the other half not. And so the main stem is really mixed, has that mixed geology influence. So with having that diverse geology, that's one of the indicators, as well as the biology, to help inform those designated uses to start with. And so again, the state, when the Clean Water Act was passed, the state then had to think about those optimal uses of the stream as it's changing throughout its entire watershed to develop that designated use. And a lot of modeling I imagine, was used to do that, because we have over 86,000 miles of stream and shoreline in the state. So yes, so a watershed, Mark, can have multiple designated uses, but we're able to hone in and use that mapping metadata to tell you what that stream segment designated use is right there at your particular site. So hopefully that answers that question. And I see Christine and Joe, another site that got called out in the presentation, have their hands raised. Good to see y'all.
You too. Thanks, everybody. Yeah, we've just been wondering, we don't, our site's, I mean, pretty vanilla in a lot of ways, but we see some movement in the conductivity. There's nothing that we can glean, or I can glean, from when that happens seasonally or unseasonally. I have no idea if even the shifts are big enough to be significant, to be indicators of something that's different. So I'm just kind of wondering, what are some of the things that might be impacting an increase or decrease in the numbers?
Okay, so let's hear your thoughts first.
Well, I mean, initially we thought, because when we first started testing, it was late fall, winter, and we were like, well, maybe it's road runoff, even though it's pretty
October
pretty
is
far,
early.
but October's kind of early. And I know water temperature itself probably wouldn't impact it too much, so it's more likely going to be stuff that's in it. But we just can't. There's not a lot of change happening in and around the neighborhood where the water's feeding down from, as far as we can tell. And we're unaware of any shift in, road management. So we're not really sure why. I would have expected to see it blip back up again seasonally, maybe, but it doesn't at all. So, or it does, but not to that extent when we first started monitoring.
Okay, so something that's really fascinating about your site, Abraham's Creek. First off, so you are
See, we're not
8.79.
vanilla.
Yeah, well, I think a unique feature is, as Greg John was pointing out, he's at a site that drains very little. He's 20 yards away from the source, right? So you are 8.7 miles from the confluence of Abraham's Creek into where does it flow next?
Goes from here into a lake.
Okay,
Into
the reservoir.
It feeds right into a reservoir in the lake. Yeah,
That's what I
State
thought. I
Park.
remember. Gotcha.
Yeah.
The other thing to point out here, so where you are draining only 3 square miles as well. You're in a place that is non-carbonate. And even like within that 3 square miles, you can see that 56% of that are natural areas. You only have 5% that is developed, and then 40% is agriculture. So, and what are types of things, and you highlighted this in your comments, like, well, what are those things that might spike conductivity? And we look for those inorganic compounds. So like road salt. Could road salt potentially result in a spike? We're not really seeing that. But yeah, so Candy, I see you're unmuted. Do you have other thoughts you want to throw out there? But those are the types of things I'd be thinking about. But is there space for impact would be a question I have. Yeah.
The only other thing I can throw in is that flow can also impact conductivity. In other words, if you have a major rainfall and you have a lot of runoff going into the creek, it could actually dilute conductivity during a short period of time. So very high flow. And there's two things that happen with high flow. One is more stuff comes in. So if you're in the city or something, very often high flow will actually increase conductivity because more stuff comes in. But if you're in a more rural area, very often the flow, it'll bring some stuff in, but overall it will dilute what's in there, and you'll get a drop in conductivity. So if generally speaking, if you plot flow versus conductivity, they tend to be inversely related to each other.
Okay.
So you might look at that too, just to be sure. And then now that we're going to start to do stage, that'll be useful to see. I know when we had a Marcellus Shale project, and we did do stage and conductivity, and for not all of them, but for many of the streams, there was a pretty strong inverse relationship.
Yeah, but I would say, you're in a very small, you're draining a small watershed, 3 square miles. You look at your other values, you have some other vanilla in there as well, as you called it. Looking at your nitrate levels, it's all in that background range, but you might have a fun storyline with temperature. You might be able to be like, I can relate to what Candy was saying earlier today. But yeah, the scope or the ability for impact from that drainage area and what you have there, and not knowing what your site looks like to know if there's road crossings nearby. We're not even seeing, we had that one stream team open call in March where everyone was talking about how their conductivity levels went up during their February sampling because the sampling weekend was right after a big snow dump throughout the Susquehanna watershed. And we're not even seeing, like, that's still pretty consistent with what you have. So it might be indicative of, not a lot of impact up there too. So, yeah. So,
okay.
But that's a story in and of itself. And as you think about preparing your slides for the June meeting, that's a storyline as well. So yeah, great question. I feel like I saw some other comments in the chat come up. So Brian, would you like to speak out your question here?
I'm just trying to figure out if we know there are major potential changes coming to a creek that we're monitoring. Is there a way to kind of, I don't know, communicate that or anticipate that? Because, you know, obviously the importance of the water quality monitoring will be more significant in the sense of what are the effects of this change to a water, you know, quality in the stream. For example, that I pointed out was in York County, we know that there are changes along the I-83 roadway that they're expanding it, and one of the changes is relocating a portion of Mill Creek, which is one of the sites that Mark and Latisse monitor. So I just wanted to throw that out there. Is that something you're taking into account, or is that I mean, there's development going on everywhere. We know there's warehouses being built everywhere, but just wanted to put that out there. Something is another variable we should be thinking about or anticipating and tracking. And because if we are looking at the effect of land development on our streams, those things are important to note.
For sure.
And could we start reporting that or tracking that if we know things like that are changing?
Yeah, I think that's a really good point. And you know, something that actually to date we haven't created a lot of space in conversations with everyone to be able to talk about, like, what are some of those anticipated impacts to streams, good, bad, what have you. Like maybe there's a restoration going on, or, you know, a tree planting's been scheduled, or there might be a situation where a road is being expanded and that might be impacting a site as well. So I think that would be a really great thing to incorporate into the slides you create with your findings for the June meeting, is also, you know, notable nuggets, changes to the stream, things to keep our eyes on, you know, in the pipeline, so to speak. And the reason why I pulled up the loser in Lackawanna land use map, and I said this in the chat as well, in part because you had talked about the 81 expansion, but you can get the sense of where 81 is, or major roads going on with this nice strip of towns and cities all clustered along. I feel like there might be a roadway connecting all of those, but I would let you all answer that for me. But yeah, Brian, I think it's a really good point. And I also think that the open calls, when you see those being advertised, definitely we create that space for conversation, reflection on our sites. That would be a great time to let us know if there are changes in your watershed that we should be aware of. And if you're not able to make those open calls, if you can email the stream team email that we have at Dickinson, or, you know, let Stephanie know or one of us know, that's also something good to know. And then the other entity I would say is where everyone is monitoring, there is a river keeper, whether that's Ted Evgenitis in the lower Susquehanna or John Zatansky in the middle Susquehanna. I would also make sure that that's on their radars as well. So, but yeah, let's start creating that space for sharing around potential changes to the watershed that could impact our water quality data for good or for maybe bad. So thank you for sharing that. And also, Stephanie and Phoebe, if you can also help keep an eye on the chat and let us know if we're missing any questions.
There's one here about seasonal declines in the water table, the impact on conductivity. Does anybody have any easy questions?
I know, Andy, come on. Maybe, yes, we know the Latort's losing some of his water. So,
That's such a good question.
oh, it's so good. Yeah.
Yeah.
Oh gosh, yeah. Yeah, that's gonna require a little more.
I do think the flow issue is something worth exploring, and maybe you guys have done this. I mean, first off, thanks for putting all that data together. It's just wonderful to see it all laid out so neatly. But one thought I had is another bit of data to overlay here is a data on flow to see if there's a correlation. Have you done any of that?
No, we have not brought flow into the equation. Yeah, which is a really important reference point. But that is also one of the reasons why, Andy, we're bringing stage into Stream Team, is so that we can have at least a water level reference point. It's not flow, but it helps to add a little addition. It helps to add additional context to the data.
Yeah. Well, gosh, don't take this as like saying you guys should have done this. I mean, thank you for all the work you do. But I mean, on the Kano, we're fortunate we have at least the one gauging station near Hoagstown Run, the USGS station. And I mean, using that as representative of the stream, it'd just be interesting to use that to take a look at some of the variability in the conductivity. And do you think the nitrogen as well? Might there be an influence there as well?
Definitely.
Dilution?
Yeah, for sure. Yeah, and just I want to put out two things, Andy. So one is flow is a very tricky parameter to do well with accessible methodology. So that is one of the reasons why stream stage and getting that water level measurement is one of the approaches we use. So if there was an accessible technique, we would have brought that in a while ago. But we are always looking at different approaches of how can we have an accessible, affordable flow technique. But yes, ideally we would have that built in. And the other thing to point out, and we said this a little bit in the beginning, like this is the start of data analysis, right? So starting to set the context for values. And, you know, as we were chatting about with Candy, like, you know, understanding the values at your one site is one thing, but we really should get to the site to site comparisons. That helps to add in the other storyline. And then, you know, being able to do some fancy footwork, you know, looking at additional gauging stations or using USGS stream stats to further contextualize is additional time and resources to put into something like this. And so definitely curious to be able to find accessible ways to bring in things like flow for sure. But yeah.
It's been trying to do flow has been, you know, a challenge for 30 years, figuring out a way to do it meaningfully. And as I mentioned before, in the Marcellus Shale project, it was really useful, even though it was just stage, it was really useful to see the relationship of that and other characteristics. I mean, it allowed us to say, oh, the conductivity here, the reason it's so low is because, you know, our flow was so high, or, oh, the reason it's same thing with nitrate. But the other thing that's important with flow is that, you know, you're measuring the concentration, and what is really important for the stream is the load, like how much total nitrogen there is in the stream, not just how much there is per milligram of, per liter of water. And so if we had flow, we could actually calculate what we call load, which would be very useful. But as I said, it's just been a challenge. And if anybody wants to take it on, other than measuring stage, we can do that, but you can't really calculate load from stage. But on the other hand, stage is useful. It's definitely useful. So yeah. So we've been struggling with that for a long time.
Yeah, not an easy answer there. Yeah, and Jeff, yes, we can start, since you have been getting water level measurement already, we can add that into the next data analysis that happens. And depending on your technique, so one of the things you all will see with the gauge sticks is it's actually in tenths of feet. So if you happen to be using a tape measure or thing like that, we have a easy conversion to go from inches into the tenths of feet. So, but yeah, we can get that and incorporate that next year for sure. Awesome. Other questions? Have folks had a chance to start looking at their data? It sounds like a few folks have, getting a sense of maybe not as exciting storylines, or maybe great robust indications of like, way to go, Abraham's Creek. But yeah, other questions as folks have looked at their data packets and the data for their site? And also, if you get EPA and USGS in the room, there's a fun battle about point in time measurement, parts per million versus the load. So whenever I talk to my EPA colleagues, they're like, those point in time measurements count. It's USGS and they're loading. It all tells good stories. So just recalling a conversation I had with someone who's at OWOW, Division of Water at EPA. Greg John, I saw you unmuted yourself. Did you have another question or comment, or anyone else?
Accidental unmute.
Oh, okay. Other questions? Because the other thing we can do is start talking about those next steps and then see if there's any follow-up. Hey, Don.
Hello, how are you?
Doing well. I love your background picture.
Oh, thanks. Since we weren't included in the data that was sent out, and I assume that's because of the length of our study so far.
Yes, it is.
I've been working on doing the same thing you're doing and trying to put some graphs together for watershed people in my area. And they also want to do a kiosk with information on the stream and runoff and what gets monitored and how it's affected. So would it be possible, once I get this little bit of information together, to go over it with somebody in the office?
Yeah, absolutely. And Don, we should have absolutely covered that in the beginning of the presentation. We were not trying to exclude Big Spring from the process.
I figured that out.
Yeah. So we did set this, we always like to have a year's worth of data before we do this, but we do actually have preliminary plans and some initial legwork has been done for those of you who were trained over the summer of 2021, because you're getting close to that year point. So yes, so one, thrilled that you've already started to do this with your data, and two, happy to chat about what you're finding, especially if I don't know if that's a kiosk you're working on with like the Big Spring Watershed Association or yeah. Let's talk about that. I mean, Big Spring, oof, you've had some interesting water quality storylines over the past few decades.
Yeah.
So yeah, absolutely willing to chat further about that.
Okay. Thank you. I actually sent Stephanie an email kind of asking the same thing. So you'll find it.
Yeah, and also a reminder about, this is back from your Chesapeake Data Explorer training. If you click on the interactive map, if you click on your station, you can pull up what's called quick plots, and it'll plot your data for you, and you can actually export that plot. And so that's a graph. You can actually export the graphs of your data in real time. So let's say, we did the end of 2021, you're interested in what these past few months were, you can go on and look at that.
Yeah, I tried that for some reason. It worked one time, I think, when I first started to learn it, but when I tried to do it this past week, it wouldn't come up. So I don't know what I did then and what I tried to do now, but it didn't work.
Could be a maintenance. Data Explorer goes into maintenance
It
sometimes.
could be, they might have been working on something.
Yeah.
That's all right.
Awesome. All right. Well,
yeah.
let's cycle back Don for sure on that. But yeah, Stephanie, could you walk us through what to expect and what the next steps are?
Yeah. So you just got a great background of all the different influencers in your water quality, the different, yeah, that one. All the influencers of your water quality and the different state standards and what your graphs and maps all mean. So in the next few weeks, we are going to have office hours. And this is going to be a 30-minute period for you to be able to hop on Zoom with the Alarm team and be able to ask questions. And we really encourage you to do your own self-discovery before you do this. You know, dive into that data summary, try to ask yourself the questions that we started asking you today and bringing up today. And so I'm going to talk a little bit about that next. But another thing to highlight in this process during this time where you're thinking about your data and doing self-discovery and asking questions is we're going to send out a template in PowerPoint for you to be able to create a summary of your findings. And so this would be a way for everyone to have a standardized, we like everything standardized, a standardized way for you to show the stories in your data. And we're going to put that all together before our June meeting. So, and I'll remind you of that for June 3rd. And then our June 8th meeting is when we're going to reconvene. And we're going to discuss and present our data findings. So yeah, Julie, you can go to the next. And so as I mentioned with the office hours, we would love to hold these during times that you're available. And we started thinking about times that we were available and realized we need to get your perspective and what would work best for you. So I'm actually going to launch a poll in Zoom. And we would love for you to note which timeframes you'd be interested in attending data interpretation office hours. This would be during the week, Monday through Friday, and you can choose more than one answer. And Julie, while they are doing the poll, do you want to go to the next slide, please?
Cool.
And this, we just want to show you, this was like one idea that we had for the times that we were initially thinking. And then again, we revisited, oh, wait, we need to hear from you all and find what's going to work best and when are you available. So you do not have to write down these dates. These will not necessarily be our data office hours. But while I have you here, it is important to note, if you haven't noticed already, that we have a stream team email. So please make sure you have that in your address book. And that'll be important for when you're scheduling these office hours. And I'm going to give it a few more seconds for you all to put in. I have about half of you have answered.
Yeah, and while we're letting folks fill this out, I just want to draw attention to a question in the chat from Marie. So for folks that were onboarded in the summer of 2021 or just last month, there's no expectations to be developing analysis on your data. So no, so for folks who have received data packets, and Don, if you want to go ahead and join in on this too, please do. But no, this is for folks that have had at least a year's worth of data collected.
Yeah, thank you, Julie.
Yeah, so thanks for weighing in on those potential office hours. Is there anything else with the slides? Should I move on to the next slide, or is this it, Stephanie?
I think that's it.
Awesome.
I think it's a wrap-up slide.
Okay, cool. Are there any other questions, comments? As we're waiting for the last few folks to add in their responses. Well, so yeah, thank you all so much for taking the time to participate tonight. You know, it's so fun to start the process of looking at your data. And yeah, if folks don't have any other questions, we'll go ahead and bring this to a close. But I want to thank you all so much for your time and dedication collecting water quality data and being with us tonight. You are the ultimate Susquehanna Stream team. So thank you so much.